Having seen detection, we'll now move on to segmentation of images using CNN architectures. We'll quickly review the exercise from the previous lecture. Given two bounding boxes in an image, an upper left box which is 2 cross 2 and a lower right box which is 2 cross 3, an overlapping region of 1 cross 1. What is the IOU? This should be a simple one. So you have an upper left which is 2 cross 2 and then you have a lower right which is 2 cross 3 with a 1 cross 1 overlap. So the total number of boxes here are 9, of which the intersection is 1 box. So your overall IOU would be 1 by 9. And the second question, consider using YOLO on a 19 cross 19 grid, 20 classes, 5 anchor boxes. The output volume would be, remember we said it is S into 5B, that's the number of anchor boxes, plus C, number of classes, and that's the final answer you get. We assume here that C, the number of classes, also includes the background. If you want to have background as a separate class, then you'll have to add C to be 21. So let's recall image segmentation in the first place. Early on in the lectures, we talked about different image segmentation methods such as watershed, graph cut, normalized cut, mean shift, so on and so forth. To an extent, these methods inspired early versions of CNN architectures for tasks such as detection and segmentation. In fact, RCNN, which uses selective search to get region proposals, in fact used a min-cut segmentation method known as CPMC, constrained parametric min-cuts, to generate the region proposals. But we'll now move on to deep neural networks for segmentation. So the task at hand for us to start with is going to be semantic segmentation, where we'd like to assign a class label to every pixel in the image. How do you solve this problem using neural networks, in particular convolutional neural networks? We're going to cast this as a pixel-wise classification problem. While so far we spoke about image level classification, where we had only a label at the level of an image. Then we went to detection, where we had labels at the levels of bounding boxes, where we not only gave class label but also an offset to the bounding box to make a final prediction. But in semantic segmentation, we are going to classify at the level of every pixel. So for each image, each pixel has to be labeled with a semantic category. So you can assume that creation of a data set for semantic segmentation is very annotation intensive. There have been various architectures in recent years such as FCNs, SegNet, UNet, PSPNet, DeepLab, MaskRCNN. We'll cover each of them in this lecture. Starting with FCNs, or fully convolutional networks for semantic segmentation, which was proposed in 2015 and 16. They adapted various classification networks such as VGGNet, GoogleNet, so on and so forth, into fully convolutional networks by converting the FC layers into 1 cross 1 layers. We saw that with single shot detection methods. It's the same idea here, because for semantic segmentation, you still have to classify at the level of a pixel. So you do not want to move away from the convolutional regime. What do? To obtain the classification for each pixel, we can have a 1 cross 1 convolutional layer at the end of any CNN and have C+1 channels in that final output volume, where C is the number of classes and the +1 is for, say, a background class. But do you see any problem with this approach? There is a problem when you use convolutional layers, which is all standard CNNs keep downsampling as you go further down the layer, be it through convolution or through pooling, which means your output feature maps are not going to be the same size as your input. But we finally want to give a pixel level label in the input resolution, in the input images resolution. So what do? We already know the answer. We can upsample after a certain stage. So you have convolutional layers, and after a certain stage you upsample and bring the feature maps to the same dimension as your input image. How do we upsample? One of the methods that we have discussed before is transpose convolution. Let's quickly recall transpose convolution. So this was the one-dimensional example we spoke when we discussed convolutional neural networks. So where your output can be larger than your input. And here is the illustration that we gave for transpose convolution, where you have a dilation in your convolution when you take the filter and apply it on an input image. Because there is a dilation, transpose convolution is also known as dilated convolution, or it's also sometimes referred to as at-risk convolution, as we will see a little later, because it dilates while you perform the convolution. So now in FCNs, this is the idea that's used to upsample after a certain level. Let's see an FCN architecture with a VGG backbone. So if you have a VGG16 backbone, the first thing that was done in FCN is to remove all the fully connected layers. So what you have now are only the convolutional layers of VGG16. So you can see all the standard feature maps of VGG16. The three FC layers are replaced with 1D convolutional layers, and the last 1D convolutional layers has C+1 filters. So you can see here the last one has 21 dimensional filters. This was applied on a data set that had 20 classes, so it was 21 dimensional. However, you notice here that while you have 21 channels, the output is still smaller in size when compared to the input resolution. So you finally have one upsampling layer which is done using transpose convolution to get back to the original size. This is what was done in fully convolutional networks. However, is transpose convolution the only way to obtain the upsampling? Not necessary. We can do several things, including skip connections, which we will see later. But before we go there, we will talk about another method that came around the same time as FCNs, known as segnets. Segnets are what you see here in the image. You have an input image, you have an output, and the architecture is a fully convolutional encoder-decoder architecture. How is this different from FCNs? Very similar to FCNs. The encoder is VGG16 without FC layers. The decoder maps the low resolution encoder feature maps to input resolution. Here there is a difference from FCN. FCN had only one upsampling layer towards the end, whereas Segnet has a sequence of decoder layers which mirror the architecture of your encoder. So the encoder and decoder architectures are mirrors of each other. The important contribution in Segnet was to avoid transpose convolution in upsampling. So how does Segnet do the upsampling in that case? It actually uses the pooling indices that were obtained in the encoder layers and uses them to be able to upsample. Let's see how this is done. So if you had an output map from a particular decoder stage, we use the max pool indices from the original encoder. So let's assume the max pool indices were 0, 0, 1, 0, 1, 0, and 0, 1. So A would go to the 0,0th location, which would be the top left. B would go to the 1,0th location, which would be the bottom left. C would go to the 1,0th location, which would be the bottom left. And D would go to 0, 1, which would be top right. Now this becomes an upsampled version of a previous layer's output map in the decoder, and one can continue to do this to get your final upsampled image. What do we mean by max pool indices? In your encoder, whenever you had a pooling layer, you keep track of the indices of which of those entries in a 2x2 patch or a 3x3 patch, depending on what pooling you're doing. You store the winning indices in a separate memory buffer, and we're going to use that max pool indices to upsample back to higher resolutions. Why is this good? Storing max pool indices is more efficient than storing full feature maps of the encoder. And in each stage of the decoder, the max pooling indices of the corresponding encoder is used to produce the upsampled feature map. So if you see the complete image, the pooling indices of this encoder feature map goes to this decoder, this encoder's feature map goes to this decoder, and so on and so forth. What is the loss function? So we've seen a couple of architectures now, FCNs and segnets. What would one use as a loss function to train such networks? Simple. It's the sum of pixel-wise cross-entropy losses. Remember, in both FCN and segnet, your output is going to be a volume, which would be the size of the input resolution, but the number of channels would be the number of classes plus 1 for background. So you can actually have for each pixel a vector of probabilities which is in your output volume. Now you could compute the pixel level cross entropy for each pixel. You can sum all of them up, and that becomes your loss function, which, because it's a sum of cross entropies, will remain differentiable. A third kind of architecture, which also came in the 2015-16 timeframe, is known as UNet. UNet is also a fully convolutional encoder-decoder architecture, but it introduces the concept of skip connections in a different way from segnet. In the contracting path, that's the encoder path, is an existing classification network with FC layers removed, similar to segnet and FCNs. But in the expanding path, in addition to upsampling of feature maps, the network also receives corresponding feature maps of the contracting path along with further convolutional layers. Finally, at the end, you have a 1x1 convolution with C+1 channels, where C being the number of classes. The upsampling in UNet is performed using transpose convolution, 2x2 transpose convolution with stride 2 and padding 0. And the number of feature channels are halved in each upsampling step, which means the total input dimensions will double now. With a 2x2 transpose convolution and channels being halved, the total input map dimensions will double at this time. So in the original UNet architecture, unpadded convolutions are performed, which means the output segmentation is smaller than the input by a constant border width. Let's look at the visual. So here is the UNet, and the shape of it tells why it's called the UNet architecture. You can once again see the contracting path is similar to any other architecture without FCN layers, and in the expanding path, in addition to doing transpose convolution at each step, you also receive the corresponding feature maps of your contracting path, which is added to your expanding path. So that gives a localization information from the encoder to each step of the decoder beyond just upsampling. So you get additional information from the corresponding layer of the encoder rather than rely only on upsampling as in segnet or FCNs. UNet was originally proposed for biomedical image segmentation. It was in fact published in a medical conference, MICI. How do you think this can affect the learning of the unit model. Biomedical image segmentation has some unique challenges. Firstly, often you do not have training data sets which are of the order of 1 million or even tens of thousands. Very few training images may be available. So this particular work employed excessive data augmentation by applying elastic deformations to available training images, which was one of the contributions. Another challenge in the medical domain is there could be many objects of the same class touching each other, because there could be objects which are similar to each other placed next to each other. So UNet also proposes a loss function which penalizes pixels closer to edges more than pixels away from edges. Edges are extremely critical for medical image segmentation. Over the years, there have been several variants of UNet, mostly by changing the architecture by replacing the convolutional blocks with dense blocks and increasing the depth of the UNet, so on and so forth. Another network used for segmentation is known as the PSP net. And the PSP net starts by asking the question, what challenges could you face if you applied FCNs on complex scenes? If you think deeper, you would notice that FCNs do not learn patterns that are co-occurrent. For example, we know that cars are on roads while boats are on rivers, and FCNs can also predict parts of an object as different categories. For example, it can look at a skyscraper and think pixels belong to different buildings because of the sheer scale of that object. Thirdly, FCNs could fail to detect large objects or small objects depending on the architecture and the receptive field employed in the architecture. So how can we address some of these constraints? PSPNet hypothesizes that one should use global context information to improve segmentation performance. So how do you get global context information? Segment at multiple scales. So when you segment at a lower resolution, you're actually trying to bring more global information into the segmentation result. So PSPNet introduces a pyramid pooling module where, given an image, you forward propagate it through a CNN, and then there is a pooling layer that pools at multiple scales. What are the different scales? There is a coarse scale, which is simply a global average pooling. So this would be 1 cross 1 cross C, where C are the number of channels. And each successive pooling level gives increased localization information. So you would have your pooled outputs to be 1 cross 1 cross C. That's the global average pooling. So each of the C channels here in the convolutional output feature map, you would take that channel, global average pool it, and get one scalar. And for each of these C channels, you would get 1 cross 1 cross C. Similarly, 2 cross 2 cross C, 3 cross 3 cross C, and 6 cross 6 cross C. And those are the 4 scales that PSPNet employs. Remember that when you do pooling, typically the number of channels do not reduce. You operate channel wise. So once these 4 scales pooling is done, the PSPNet now applies a convolutional 1 cross 1 convolution on each of these maps that came from the pooling operations to reduce the number of channels in the output. By how much does each of these 1 cross 1 convolutions reduce the channel size by? By 1/4. There is a reason for that. The reason is once these 1x1 convolutions are performed, all of these are upsampled and concatenated. So each of these pooled maps are upsampled using simple bilinear interpolation, and then they are concatenated, and this concatenated volume is going to have the same number of channels as the original feature map. Once this is done, this is then sent through a convolutional layer to get your final prediction of segmentation. Another method is known as deep lab, which is a popular method for semantic segmentation, which is similar to PSPNet. In this case, the image goes through several blocks of convolution, and then instead of having a pooling layer which splits the image into 4 different scales, it performs address spatial pyramid pooling. So this module is known as the ASPP module. Remember, address convolution is the same as dilated convolution or transpose convolution, or sometimes even called fractionally strided convolution. So when your stride is less than 1. So then you get the same effect as performing pooling at multiple scales. So address spatial pyramid pooling, you could say, is a different way of implementing your pyramid pooling module in PSPNet. So once you do your address spatial pyramid pooling, you once again upsample, concatenate, and you finally get your result on that concatenated volume. Deep Lab has gone through a few different versions over the years, and one of the more recent versions, known as Deep Lab v3, adds a few modules to the basic Deep Lab architecture. In this Deep Lab v3 module, image level features are also passed on to the ASPP module. There is batch normalization, which is used for easier training, and there is also an entire decoder architecture which is used to refine the segmentation results. So you can see here that you have the ASPP module, using which you perform 1x1 convolution, 3x3 convolution, so on and so forth. You get a set of feature maps which are concatenated. 1x1 convolution is done to reduce the depth of those channels, and that is then upsampled by 4 and passed on to the decoder along with the output of the ASPP module. These are then concatenated, and you finally have one more convolution at the end and then upsample and make your predictions at the end. Remember that this when we say prediction, it is going to be again an output volume whose resolution is the same as the input image, and the number of channels would be C plus 1, where C is the number of classes plus 1 for background. Moving on from semantic segmentation, instance segmentation is a slightly more challenging task than semantic segmentation. In semantic instance segmentation, or what is popularly known as instance segmentation, our goal is to not only give a class label for every pixel, but to also assign an object ID for each of the objects. So if there are multiple people or multiple chairs or multiple dogs, you want to also separate those people, the instances of the people and instances of the dog, which the basic semantic segmentation task did not consider. In semantic segmentation, a dog would be a dog pixel, whether there were 2 dogs or 3 dogs or 4 dogs, all of them would just be classified as dog. But in instance segmentation, we want dog 1, dog 2, dog 3 and dog 4. And the challenge here is you may not know the number of dogs, which is similar to the detection problem, which is why one of the most popular approaches for instance segmentation, known as mask RCNN, actually tries to improve upon faster RCNN to achieve instance segmentation. So mask RCNN was proposed in ICCV of 2017, and it uses a faster RCNN like architecture but adds a branch to also mask out and get instance level segmentation. So you could look at mask RCNN as faster RCNN with FCN on the regions of interest. It adds a parallel head along with your SVM object classifier or simply your classification module and your bounding box offset regressor. You now add a mask predictor. That's a third head. An important contribution in mask RCNN to be able to achieve the mask accurately was a module known as ROI align. And since mask RCNN operates in the framework of faster RCNN, the main limitation of faster RCNN that this module addresses is that when you map object proposals to feature space, recall that both in fast RCNN and faster RCNN, you had certain object proposals and you mapped them to a certain feature space. And feature space could be of a different resolution than the resolution in which you obtained your object proposals. In both fast RCNN and faster RCNN, we simply warp it to the size required and then bring your object proposals to that dimension. However, when you do something like this, you could face errors due to quantization. Why does this matter? This matters because one pixel in feature space could be equivalent to many pixels on an image because the feature space is smaller in later convolutional layers when compared to the initial input. When you try to get a mask, these few pixels can bring a significant error in the final performance. So how do we overcome this problem? ROI align performs bilinear interpolation to get the exact coordinate for the locations where the object proposals match to a given feature map. This preserves translation equivariance of masks. What do we mean? We mean that given an image where an object could be located in this yellow box or red box, both could be valid detections, but the mask position in each of these bounding boxes is different. So by translation equivariance, we mean that if the object has moved by a certain amount inside the bounding box, the mask also has to move by the same amount. And this can be achieved by the ROI align layer. So the way ROI align does it is when you convert your object proposals to locations on your feature map, if the location turns out to be in between a few pixels on your feature map, then you perform bilinear interpolation of the pixels around the feature map, and then you get your specific pixel value at that specific point pointed by the object proposal, and that is what is then pooled to get your fixed dimensional representation that goes to later layers of your faster RCNN architecture. So in addition to your standard faster RCNN architecture with a classification loss and a bounding box loss, we also have a mask head with the mask RCNN. And what the mask RCNN does is it uses an FCN kind of a branch, so which means it's fully convolutional. And for each ROI, the mask size is 28 cross 28, as you can see here. And it's finally rescaled to the bounding box size and then overlaid on the image during inference. So this mask, as you can see here, is obtained for every ROI and then finally overlaid back on the input image at inference time. A last and more recent form of segmentation that is popular is known as panoptic segmentation. Panoptic segmentation combines semantic segmentation and instance segmentation. So semantic segmentation, as you can see, is where you segment the pixels of all objects, but all instances remain the same. Instance segmentation is where you only care about the instances of the objects in your categories, but you label each instance separately. And panoptic segmentation is the union of the two, where you label every pixel as belonging to different objects, and you also ensure that each instance of an object gets a different label altogether. So how do you perform panoptic segmentation? So this work was first introduced at CVPR of 2019, about a year old, and one could achieve panoptic segmentations using a couple of architectures. So you could perform mask RCNN to get instance segmentation results. You could do a dilated FCN to get semantic segmentation results, and then you merge the two to get panoptic segmentation. That's one approach. So this particular work actually implements a couple of approaches and then studies how this needs to be evaluated differently. So another approach is you could take a feature pyramid network instead of what we saw here. Instead of using a dilated FCN or a mask RCNN, you could use an FPN, a feature pyramid network, and then send those detections through a mask RCNN head to get your instance level segmentations. And you could also send those different feature maps through a pixel level recognition head to your semantic segmentation. So in both these approaches, there is an instance segmentation pathway and there is a semantic segmentation pathway, which are combined to give your panoptic segmentation. What would be the loss function here? The loss function recommended is a combination of both semantic segmentation and panoptic and instance segmentation. Remember that instance segmentation, the way we saw with mask RCNN, has three losses: classification, bounding box, and the mask loss. And then for semantic segmentation, you have your standard pixel wise cross entropy loss. One of the challenges of panoptic segmentation is that it cannot be evaluated using the metrics one may use for semantic segmentation or instance segmentation. Why is this so? In semantic segmentation, we use IOU and per pixel accuracy. So you can try to see if you drew a set of pixels that belong to a particular object, you could try to get the intersection over union with the ground truth of that object. You could also get a per pixel accuracy because you're going to predict probabilities at each pixel level for all the classes that you have. You can also look at that accuracy as a metric. On the other hand, for instance segmentation, which is similar to detection, you would have average precision over different IOU thresholds. Why cannot we use these for panoptic segmentation? That's because this could cause asymmetry for classes with or without instance level annotations. Remember that in panoptic segmentation, you could have certain classes where there are multiple instances, for example, people or dog, and there could be certain classes such as sky, road, which may not have many instances. So to combine these metrics without considering these asymmetries may not be wise. So this particular work recommends a new metric known as the PQ metric. How does the PQ metric work? You can look at this example here. Let's assume that this is your correct ground truth. So there is sky, there is grass, there are three people, that's the instance segmentation part of it, and then there is a dog. Let's assume now that whatever model we came up with predicted it this way. The sky, it got it right. The grass, it got it right. The dog became person, and instead of three people, it only predicted two people where it combined two of these people. So how do you now measure error of this kind of a system? So the way this approach recommends is you first write out all your true positives, which would be your two people, which are true positives between your ground truth and prediction. There is a false negative, which is the person you missed, and there's a false positive, which is the person you added instead of a dog. So for a ground truth segment G and for a predicted segment P, the PQ metric is computed as summation over all PGs belonging to true positives, intersection over union for those PGs, divided by number of true positives plus half times number of false positives plus half times number of false negatives. If you analyze this, this can be written as, the numerator stays the same way. Let's multiply and divide by number of true positives. Then you would get the first term to be this way and the second term to be number of true positives by number of true positives plus half false positives plus half false negatives. So the first term here gives the segmentation quality. Among the true positives, what was the IOU for all of your segments? And the second part gives the recognition quality as to among all of your possible segments, how many of them did we get as true positive. So you have a part of it that checks for segmentation quality and a part of it that checks for recognition quality, and that is why this metric becomes useful for panoptic segmentation. For more details, please read a good overview of semantic segmentation by NanoNets, a good overview of Deep Lab semantic segmentation method, which is a popular one at Analytics Vidya, and also a good introduction to panoptic segmentation.